specifically kid-inspired visual analogies for large multimodal models. And so let me just start with the idea that we don't just learn with new data, we also learn by thinking. And so even in the absence of new empirical evidence and testimonies, we can learn from existing data through explanations, through repeated practice, through making analogies, and analogical reasoning is what I want to focus on today. And so what exactly is analogical reasoning? It is drawing comparisons between different domains or different kinds of situations to understand or to solve problems. So analogical reasoning is making connections between different ideas that at the first glance might not seem disrelated. It is a mental leap that allows us to apply known solutions to new, seemingly distinct problems. We use analogies to help us understand more abstract or new concepts in science. If you studied chemistry at some point, you might have heard of the analogy between the cyclic structure of benzene and a snake eating its own tail. It is a useful analogy because it provides a vivid, intuitive image to help us conceptualize this continuous closed-loop structure of benzene. Similarly, we might find that electricity flow is analogous to water flow in physics. But we don't just do analogical reasoning in the classroom. We generalize patterns from observations to make new predictions all the time. So suppose I put a wool sweater into the washing machine and it comes out smaller. I don't just learn that the sweater is reduced in size through the wash, but I also draw analogies that if I later on decide to put like a wool coat into the washing machine, it might also come out much smaller. And relying on the observation about the sweater, I may learn to avoid putting a different item, a wool coat, into the washing machine. Or if I leave a dozen of cookies in the kitchen and I come back with only one cookie left, I learn not just that the cookies have gone down in number, but I make rich inferences about how my roommates were eating them behind my back. And so the next time I have chocolates or something that I don't want to share, I might learn to not just leave them out in the kitchen. Okay. So a lot of analogical reasoning takes place in rich and abstract observations that are not just captured in text. We don't just rely on knowledge of language or learn symbols to make analogies. There's literature out there suggesting that crows, chimps, and many other animals can also perform analogical reasoning, suggesting that language is neither necessary nor sufficient for analogical reasoning. And this is also why we care about visual analogies. But what do the visual analogies look like out there? A lot of the visual analogical problems in the literature currently look like this. We have Bongard problems, Raven's progressive matrices, which are commonly used in human IQ tests, and more recently, the ARC and concept ARC on the right, which is developed by Melanie Mitchell's team, which you'll hear from later this week. And what the finding generally is that large pre-trained multimodal language models like GPT-4b have been struggling with these puzzles. But these are all really abstract puzzles, and a human doesn't really need to solve these to get by in their everyday life and to show that they can really do visual analogical reasoning. Moreover, people and models have always only been evaluated on how well they can predict a new input based on given observations. So if a person or a model fails and gives you an incorrect answer, we don't know where exactly they're failing in the thinking process. Are they failing because they failed to read these abstract shapes and pixels properly? Are they failing because they can see everything correctly, but then cannot kind of generalize properly? Or are they failing because they can generalize to the correct rule, but then when they see a new thing, they don't know how to apply to a new situation? So we take a step back and ask, what are some more fundamental visual transformations that are important to know in everyday lives? What is something that even a 3-year-old can possibly notice and understand? And there is work in our lab suggesting that a 3-year-old can understand these kinds of visual transformations, which is just simple size changes, color changes, number changes, rotation, and reflection. And so we developed this benchmark where we create common child-friendly 3D objects from big object data sets, as you can see here, and we transform them in these very simple ways. We argue that this is also closer to the model training data than, say, 2D grids and abstract line drawings. And we have over 3,000 stimuli generated in our benchmark, but the number of stimuli you can generate is really infinite. Anyone can take any object they like and apply this kind of basic visual transformation using just a Python pillow package. Okay, And so to give you a sense of what the test looks like, let's do a simple test to see if we're at least as smart as the 3-year-olds. So here we have a cactus, and then it turns into this cactus. Now we have this fridge. What is it going to turn into? And so you probably can tell that it's going to turn into this other fridge that's faces another way. And congratulations, you did a visual analogy here. And this is something that we really show that a 3-year-old can also do. And so these are our participants in this study. We have 40 adults and 30 children aged between 3 to 7 years old. And they complete a random subset of the benchmark. Adults get extra money and children get stickers for getting correct answers, but they don't get the feedback until the very end. So we're not teaching them visual and logical reasoning in the process. And then we have GPT-4V, Lava 1.5, and Mantis, which is an interleave multi-image instruction tuning model doing the same task. And each query is repeated 3 times, and we just average the performance across. And so these are the transformations we examined. And this figure might be a little bit confusing, but it is not a generative task. It is a discriminative task, which I'll show you in a moment. So we developed this automated step-by-step evaluation process. We start with a system message, which we call the models an expert in visual puzzle solving. And then we go on to show our different kinds of stimuli. So we break it down step by step in our query. So first, we show them an image on the left that turns into an image on the right. And then we ask the models and people, do you see a change? And if so, what kind of change it is? So you see here the options we have are like maybe a change in color, change in size, no change or doesn't apply. And then if they get this change identified correctly, we then go into something more specific and say, what exactly do you think the change is? Are things becoming bigger? Are they becoming smaller? And so this is really to get at where they might be seeing things properly and not. And we use multiple choice to automate this evaluation process. And then we have the extrapolation phase, where we have the original image, and we say, OK, here's like a new object that goes through the same change. So which one of these options here shows the same change as the one we just showed you? And so again, it's multiple choice, as you can see. And so, yeah, just to outline the pipeline a little bit more and the exact wordings we use, it's a lot of words, and I'm happy to show you more after the presentation. But basically, we have a cross-domain query and then a within-domain change detection query, and then we have an extrapolation. But if people and models are not able to generally recognize the change correctly, then we just skip directly to extrapolation, and we don't show the within-domain change detection question. OK, so what do the results look like? Well, on the y-axis here, we have the average score. And on the x-axis, it's a little bit small, but we have the different kinds of transformations. So number change, rotation, reflection, number change, color, and size. And what we have color-coded are the different question types. So we have cross-domain change detection, within-domain change detection, and extrapolation, which is what people generally measure in visual and logical reasoning. They don't really check the previous steps. And what we see with adults is they do really well. And children are also doing really well, a little bit worse, but they're still significantly above chance. So extrapolation would be at 33% chance if it's chance level, and they're significantly doing above that. I haven't collected enough data to show any kinds of age differences, but in general, we see that 6-year-olds are at ceiling, and even 3-year-olds are correctly doing this thing significantly above chance. And for most of the concepts, the middle yellow bars and the green bars are not significantly different, which means that if people can map on in words what exactly the change structure is, they can then extrapolate it visually to a new image. And so what do the models' performance look like compared to the humans? And so here, this is what GPT-4V's performance look like if we feed everything in a single image. So like the query image and also the options of the new input object. And so what we see here is there's plummets in performance going from recognizing a general change to recognizing the specific change, and then going on to extrapolation. And so they're not doing this thinking process really faithfully like humans are. And when we try to like just feed GPT-4V multiple images, maybe because it's a resolution issue, right? So we tried this as well. We don't see that performance is changing that much. And we see very similar performances of Lava 1.5 and also with Mantis. So they're overall all not doing very well in this extrapolation process. Even when they can read things really properly, there's still like this drop in performance as they go on in the process. Okay, so this is just a spidergram to really show you how the different performances are for humans versus the models. And what we have here is how well they are at visually extrapolating a single transformation to a new object. So we can see that the adults are at ceiling, kids are doing really well, and there's really this difference, very significant difference with the model performance. And interestingly, we also noticed that what is hard for GPT-4v seems to be hard for adults too. So what we did here is we took the average response times of adults and the different kinds of transformations we tested. And these are all color-coded by the different concepts. So rotation is in red, so on and so forth. And we also took the average of the errors made by GPT-4v. And what we see in this graph is if we're telling people and models to identify specifically what the transformation is, humans are taking longer when they're identifying rotation and reflection. And the models are also making more errors there. And by contrast, humans are very fast at recognizing color and size changes. And models also make fewer mistakes there. And this is true for the extrapolation process as well. So it seems like this is a little bit domain specific in the sense that rotation, reflection, 3D spatial transformations are harder. And things like size and color seems to be easier for both humans and models. Okay, so can we make the models better at visual analogical reasoning? What about presenting them with more training data? What about making prompting in different ways? So we tried different kinds of text prompting. We tried instruction prompting, which is to ask the models to write exactly the instructions of how a transformation has occurred. We tried inference through code, asking the models to write the code of how the transformation might have occurred. We tried self-reflect as well. And there's no improvement across all of these different prompting techniques. The other thing we tried is in context learning. So we tried to provide 6 to 10 example puzzles from the training set with explanation of why this is the answer. So for instance, you can see an example here. We say, OK, solution B is the answer because the object is flipped upside down. But we don't really see an improvement in results either here. Maybe with 10 in context examples, you can more specifically identify the change, but extrapolating things is still really hard for the models. Finally, we also tried visual prompting. So we tried changing the background color of the objects. We tried cropping and changing the object scale. And again, we don't see any improvement. We haven't given up, though, because I think there are so many more ways you can probe models and look for ways to improve performance. And reporting null results probably requires a bigger burden of proof in some sense. But moving forward, even if the models solve KiVA, which is our kid-inspired visual analogies task, we have a curriculum ready for it. So what next can we do? Well, visual analogies are really hard. And so what we have here for KiVA is that things always start with the same input value. So if I have an upright object for reflection in training, they will also see an upright object at test. If I start with 3 objects for number, then at test they're also asked about 3 objects. But then what happens is we also created this other data set, which is called KiVA adults, that has different starting values. So I might show you 3 objects at training and then ask you about how 2 objects are going to change a test. And we found that this is something that 3- and 4-year-olds cannot do, but then adults are still really robust at doing. So if models could solve the kid task, maybe they can then move on to solve the adults task. And then the other layer to it would be to add transformative conjunctive transformations, so combining objects and concepts in this kind of manner. So here you will have to dig into more evidence and look into what's the relevant rule here. And for time being, I'm just going to say it's the object type and shape being in the highest number that matters, and color is irrelevant. And this is actually adopted from concept arc as well. So we think this is cool, but it's many, many steps away and much more complex than our KiVA task, which is so basic that even models still cannot solve. OK, so to summarize, large multimodal models perform visual analogical reasoning not as well as a 3-year-old can. Sometimes it fails to recognize the specific visual details, and other times it fails to extrapolate faithfully. And it may take more than just simple in-context learning or prompt engineering to do it. And here are some ongoing questions, but because I'm out of time, I'm just going to leave them out here. And thank you so much for listening.
So So and can you go back to the results? I'm curious. So one of the things that seems to have worked well is size transformations. And as far as we know, these architectures are actually not size invariant. So is it something because of the do we know something about the training data? Not in GPT-4, obviously, but in some of the open models, do they do some augmentations for sizing and stuff like that that allows them to kind of like learn this kind of invariance? Because the architecture itself, we just take kind of like these patches. It's like the computation is just sensitive to sizing because it like just looks differently. It will go to different edges in the architecture. Same with like CNNs, right? Like everything we've done, the architectures are not size invariant. We just solve it by augmentation, I guess.
Yeah, I think that's a good question. And Shiri and I have been talking about this, about what exactly might be making color and size easier versus other things like transformations. Mental rotation or reflection might be harder. And one thing might be like global local, like you can really detect how many pixels are occupying an image with size. Like you can detect size for that. But then something like reflection or rotation, you cannot really rely on that kinds of like shorthand rule. Yeah.
Exactly, but they seem to be successful in it, right?
They are successful saying that something got bigger, which is what you would expect, right?
Oh, okay, I see.
That's exactly what you said. That you're also sensitive to color.
But they will also, but they won't necessarily see it as the same object, right? It's very easy for them to see the size.
We're not giving it that option, right? We're saying like,
Okay.
what shape? Is it a
So I'm
color
curious
shape?
if that will make it fail, if you just give it some kind of like distractors.
That's a good question we haven't tried.
Okay.
So one of your early examples, you kind of hint at the causality, right? When you have this sweater, a kid cannot tell. So it's really know the material. So when does a kid develop the sense doing analogical reasoning use causality?
That's a really good question. And there's a lot of work in our lab suggesting that even as young as toddlers, with the right kinds of experimental paradigm, they can figure out really abstract rules. A lot of our tasks involve putting things in a blanket detector, which is like a machine that would light up only under certain conditions. And so children have to actively explore what kinds of objects to put into it to make the blanket detector light up. And so, yeah, there's like a whole literature that I can share with you on that.
I think we're interested if you can design something for the kids to use causality to do the generalization.
Yeah, there's actually another work that is not mine, but from the lab, coming from Eliza Kosai, and she has been comparing blanket detectors, so children exploring blanket detectors versus large language models and reinforcement learning agents exploring blanket detectors. And so that's a work that could be relevant.
Yeah, thanks.
Awesome talk and super interesting results. So first I wanted to make a comment on the earlier question, which I think this is a really beautiful illustration of a point that was made yesterday, that we want these models to be invariant to things except when we don't, right? We want them to be invariant to size and color and object recognition, except when we don't, because we want them to understand visual analogy involving these things. I think it's a really nice illustration of that point. But I wanted to ask about the fact that they're so good at these things and whether you think that relates directly to the training data. Because it seems to me there's something about reflection and rotation that makes them not the kinds of things that are easy to talk about, angle, and not the kinds of things that humans tend to talk about when we're capturing an image. Like we don't say this is a photo of a dog facing 45 degrees to the left very often, as much as we say this is a photo of a golden retriever or something that gives you more color information. So do you think this just originates in the quality of the representations the models are getting because of their training data, or do you think there's something more fundamental going on?
Thank you. That's a really good question. And we have been talking a lot about this, and I think one very likely hypothesis is exactly that, which is that we don't necessarily caption images in terms of rotation and things being reflected as much as we call something a certain kind of color or size. And I am very curious to look at just vision models, because right now we have these large multimodal language models, but they're fundamentally driven by language. And so one thing that would be interesting to look at might be generative visual models to see if they also would have these biases, or they probably would succeed on the task. We don't know, but that'll be something to test to see what exactly is driving these differences in performance.
Great. Thank you, Eunice. So we're running a bit late. It's kind